Hello friends, welcome to the refresher course in mathematics conducted by Ramanujan College of Delhi University. I am Neetu Kumari, working as an associate professor at IIT Mandi, Himachal Pradesh. And today I'll talk about the introduction to basic mathematical models in ecology. So in this talk, I will cover the standard mathematical models of single species and two species which exist in literature and how the history of these mathematical models evolved. And eventually I'll talk about a three species mathematical model and different challenges that people or the authors face in ecological models and how do they tackle those challenges. You can actually find the details of the basic mathematical models in ecology in some of the popular books of mathematical ecology. For example, the book by John Pastor, the book by Marcotte, L. Rockwood, and another book by Upadhyay and Enger. So anyone who is interested in getting into in depth of this models in ecology can refer these books. Okay, so we will start this lecture series with the single species models. So the very first mathematical model that was proposed in ecology was by Malthus. It's known as Malthusian model, also known as Malthusian exponential model. So in this model, we assume that n is the growth rate of the population, n is the population density. So the number of individuals in any population is its population density. It is denoted by n here. So Malthusian modeled this population density with this equation 1 upon n dn dt equal to b minus d. So what is b here? B is the birth rate and d is the death rate of the population. So 1 upon n dn dt is equal to birth rate minus death rate. Now this difference between the per capita birth rate and death rate can also be assumed to be R, known as intrinsic rate of growth. So difference between the per capita birth rate and the per capita death rate is termed as intrinsic rate of growth, represented by R here. So this Malthusian mathematical model proposed in 1798 was one of the simplest mathematical models in ecology, which can be represented by this initial value problem, that is dn dt equal to Rn, with the initial population assumed to be at constant value n naught. Now if we solve this linear first order differential equation, the solution of the model comes in the form as shown in equation number 2, as n is equal to n naught e to the power rt. So what is the nature of this particular solution? We can see very easily from this picture as well. The nature of this particular solution, it grows exponentially. Alright, so this grows exponentially when your r is positive. Whereas when this r becomes negative, then there is a decay, and that decay too is exponential for negative intrinsic rate of growth. So this was the very first model known as Malthusian model, proposed in 1798 by Malthus. The details of this can be found in this paper. Moving on to the next mathematical model, which came at the time when this Malthusian model was very popular. So at that time, Verhulst Pearl proposed this particular model in 1838. So this particular model was the first explanation of what currently is known as the logistic equation or the logistic mathematical model. So the mathematical form of this model can be seen from this equation number 3. So what do we see here? The population growth rate dn dt, it is a function of quadratic term of the population size, population density n. So it's a quadratic function of the population size. It is simply also known as logistic model in literature. So here the per capita growth rate falls to 0 at the carrying capacity k, and the solution of this model can be given by this particular form, where n is equal to k upon 1 plus k by n naught minus 1, where n naught was our initial population, multiplied by e to the power minus rt, where r is the intrinsic growth rate, which is nothing but it is the difference between the per capita birth rate and the per capita death rate of the population into consideration. So this particular model known as Verhulst-Pearl logistic model, or simply logistic model, has one interesting parameter here. This is known as carrying capacity. So the carrying capacity is nothing, capital K is known as carrying capacity. So it is nothing but it is the maximum number of individuals a particular environment can sustain based on the available resources, which includes the availability of the food, which is prey, or the availability of whatever food they take. So this was the idea of this logistic model, where you have the environment has a certain value which is known as carrying capacity. Only to that extent the particular environment can sustain the population n. Then later there are some modifications done. Several research happened in a single species model. So one of the factors that was included in the single species model was alley effect. So here I present a single species model with alley effect. What is alley effect? So we'll have to first understand what is alley effect. So in order to understand alley effect, let us first define what do you mean by alley effect. So alley effect is a phenomenon in biology characterized by a correlation between population density and the per capita growth rate of the population or species. So this means it is already known that overcrowding is not good for environment. However, when there are too many individuals of a population in any area, they start competing for limited resources, for example food, space, water, etc. So without enough resources to go around, individuals can starve or they can produce fewer babies, slowing down the pace at which population was growing. But when the population becomes too small or sparse, that can endanger the species too, by making it less successful in reproducing or surviving, and hence slowing down its growth. This particular property is termed as alley effect. So this alley effect here in this particular mathematical equation model is incorporated using K naught, which is the threshold alley effect. So here 1 upon n dn dt can be written as f of n. So f of n is a function of this population density n, can be modeled something like this. So here this alley effect K naught, which is your threshold alley effect that is incorporated here, it can be categorized into two types. So the two category of alley effect can be named as, first one is the component alley effect and the second one is the demographic alley effect. So what is the component alley effect? So whenever it depends upon, so alley effect is categorized into two types depending upon whether the decline in individual fitness at low population densities concerns a fitness component or the overall fitness. So if only one fitness component of the population is affected, this is termed as component alley effect. Whereas when this overall fitness is is affected due to the low population density, then it is termed as demographic alley effect. But it should be noted that component alley effect need not always give rise to the demographic alley effect. Now this demographic alley effect can further be categorized into strong alley effect and weak alley effect. So if the growth rate of the population is initially positive, that is f of 0 is greater than 0, then it is called as weak alley effect. Whereas if the growth rate of the population is initially negative, that is f of 0 is less than 0, then it is termed as strong alley effect. Now some population poses a threshold to the growth. For example, here the threshold is k0 as considered in this particular model. So solution with initial condition above k0 approaches to k, as it can be seen from this figure. And the solution, the population which is below this threshold k0, it with initial condition below this threshold, it decays to 0, as it can be seen from this figure. Also, the per capita growth rate shows an alley effect or an increase in per capita growth rate over certain range of density that we can see from this particular figure. So in the single species model, we have alley effect incorporated also. Now let us move to the two species model, some of the standard two species model that came into literature for and it was studied rigorously by several scientists. So one of the very old two species model and very famous two species model is known as Lotka-Volterra model. So this particular model, it was proposed by Lotka combinedly, it was proposed by Lotka in 1925 and Volterra in 1926. So the form of this particular mathematical model can be seen from this equation number 6. So here the system is governed by this particular model, where both prey and the predator would undergo constant oscillations, and its amplitude bears no relation to the biology of the two species. What are the nature of the two species, whether the two populations, they are specialist type or they are generalist type, it has no connection with the dynamics has no connection with the nature of the species, two species, but only to the initial size of their population. So this was actually one of the drawbacks of this particular model, and it was very unrealistic. It has no connection with the nature of the population. So here as we can see, this dp/dt, p is the prey population and z is the predator population. So the growth of the prey population at any time t, it is modeled by these two terms here, the prey growth in the absence of predator, that is a1p, then minus total killing rate by predator, that is b1zp. So this is the number of populations who are the prey population created by the predator population z. So and similarly in the second equation, that is the rate of change in the predator population is equal to minus a2z, which is decline in the predator population due to absence of their food, and another term is plus b2pz, which is the conversion of the prey population into the predator population due to predation by the predator population z. So here this was one of the basic two species predator prey model used in literature, although it has the limitations as discussed earlier, that it completely they undergo constant oscillation and its amplitude bear no correlation with the nature of the species into consideration. Also there are a few assumptions in this particular model which was done while modeling this. So it is that neither the prey nor the predator population inhibits its own rate of growth. This means that the growth rate of neither the prey and nor the predator population. It has anything to do with its own population, no impact. Second, the environment is completely closed and homogeneous. And third is every prey has equal probability of being attacked. This means all the prey individuals are equally exposed to predation. Now later, after this Lotka-Volterra model, which was proposed in 1925, 1926, later came in 1960 another very popular model known as Leslie-Gore model. So here it is the Leslie-Gore model can be modeled as shown in equation number 7. So here the dPdt, where P is the density of the prey population at any time t, and this equation dPdt shows the growth rate of the change in the prey population with respect to time, and Z is the density of the predator population. So dz dt is showing the change in the predator population with respect to time. So here we see A1 is the intrinsic growth rate of the prey, and C1 is the effect of the density of the predator population on the population growth of the prey. So here again A1P is showing the growth in the prey population, and due to natural birth or natural growth in the population. Then C1ZP, this term shows decline or decay in the prey population due to predation by the predator Z. Then second equation here, A2Z is the growth rate in the predator population, and minus C2Z square upon P. So here C2 is the number of prey required to support and replace each individual predator. So here this factor C2Z by P tells us that the rate of growth of the predator population is limited, and it causes a decrease in the rate of increase of the predator population as Z increases. So this particular model, known as Leslie-Gore model or LG model, it leads to asymptotic solution tending to stable equilibrium, which is independent of the initial conditions and depends on the intrinsic factors governing to biology of the system. Although it's a significant improvement over the previous Lotka-Volterra model, although it is limited to its explanations in its own ways. So these were two standard, very popular two-species model which are studied in literature for the predator and prey population. Now let us move to three-species model. So most of the three-species models were based on the dynamics of the mathematical model were based on the nature of the population into consideration. So for that purpose, we will here before discussing the model in three species, let us first discuss the classification of the predators by the ecologists. So ecologists have classified predators into two categories based on their food preferences. So based on the food preferences, predators can be either specialist or it can be generalist. So what are the specialist predators? So a specialist predator is the one who dies out when its favorite food is absent or is in short supply, whereas a generalist predator is the one which, in the absence of its favorite food, switches to an alternative food option. Hence sustaining of the population happens. Although that is not the case in the specialist predator, which dies out whenever its favorite food is absent. Now there is an exponential decay of these predators, specialist predator. Mathematically there is an exponential decay whenever their favorite food is absent. And in the case of generalist predator, the per capita growth of a generalist predator is limited by dependence on its favorite prey, and this limitation is inversely proportional to per capita availability of prey at an instant of time. So some of the examples of the generalist predator we can see, which can switch to other food options, fox, cat, etc. Whereas owl weasel, they are examples of the specialist predator. So in the two species model, depending upon the nature of the population, predator population. So we have one of the basic mathematical models, which was given by Rosenwick and MacArthur in 1963. So this particular model, here the prey population and the predator population is of specialist type. So the prey population is being eaten by the specialist type predator population. So the model takes the form as shown in equation 8. So here we can see that the change in the prey population, that is dp dt, is equal to A1P, that is per capita. This is A1 is a per capita rate of self-reproduction for the prey. So this is the growth in the prey population due to new births, and this minus B1 P square represents the intraspecific competition among the prey population. So it causes decay due to competition among the individuals of the prey, and this term is the W is actually the rate at which maximum rate of per capita removal of the prey species due to predation by its predator population Z. So it follows here Holling type 2 functional response, and this is causing the loss in the prey population as per Holling type 2 functional response. The second equation is the change in the predator population with time. So this is equal to minus A2Z. So this is as described here due to predator being the specialist type. So there is a decay in the predator population due to absence of its favorite food, and there is a growth in the predator population due to predation of its favorite food P, and here D1 is and D are the half saturation constants. So this is another model which is extensively studied in ecology. Then after Rosenwick-MacArthur model, in 1975, another model that was proposed by Holling and Tanner, it's known as Holling-Tanner model, and mathematically it takes the form as shown here in equation number 9. So here how is it different from the Rosenwick-MacArthur model is that the predator is here of generalist type, which means the predator, in the absence of its favorite food or the favorite prey, can switch to its alternative option, and it will not die out in the absence of its favorite food. So here the P is the prey population, Z is a generalist predator population, and the growth of the prey population is of logistic type. It's logistic growth here, and the prey population dies out due to predation by the predator population Z, here using Holling type 2 functional response, and C is the per capita rate of self-reproduction of the genus predator Z, and this W4 measures the severity of the limitations to the predator population by per capita availability of its prey. As in the case of limited supply of the prey, there would be limitation of growth of the predator population as well. So this is minus W4 Z square upon P. Now here this is a general prey predator model. This particular model was a particular structure of a generalized prey predator model. It was given by Peter Turchin in this book Complex Population Dynamics. So here we assume Rp to be the density dependent per capita rate of growth in the prey population, and delta Z is considered to be the per capita decline rate of the predators in the absence of prey, and f of pz is the predator functional response. For example, if we assume that the predator consumes the prey population using Holling type say 3 functional response or Bedington type functional response, So that would be represented by this term f of pz here. And xi is the conversion rate of eaten prey into numerators. So here this f of pz, as I introduced here, functional response. So basically we can have, based on the nature of the prey and the predator population, we consider different forms of these functional responses in the mathematical model. So then for that we must understand what is a functional response. What do we understand by a functional response? So a functional response, are also known as trophic function of the predator. It is the predator to the prey density ratio in population dynamics, and it refers to the change in the density of prey required per predator in unit time as the prey density changes. So there are different types of functional responses that are being studied in ecology or in mathematical ecology. So some of the very standard and famous functional responses can be seen here in this slide. So here we can see first one is Holling type 1 functional response, which is also known as linear functional response, which takes the form as shown here, alpha p. And then Holling type 2 functional response, also known as Centroid functional response, which takes the form as alpha p upon p plus a. Another one is Holling type 3 functional response. It is of the form alpha p square upon p square plus a square. Then Holling type 4 functional response. So all these four functional responses were given by Holling, hence it's named after his name, Holling. So Holling type 2 functional response, 4 functional response takes the form as alpha p upon p square upon I plus p plus a. Other than that, then there is simplified Holling type 4 functional response, which is nothing but simplification of this Holling type 4 functional response. This is alpha p upon p square plus a square. Another functional response is ratio dependent functional response. So its form is given by alpha p upon alpha beta p plus z. Then these are very popularly used in the literature and is known also. Another set of popularly used functional responses are Hassel-Varley functional response that takes the form of AP upon BP plus Z to the power m. Then next is Bedington-Dietrich functional response, which is of the form omega p upon alpha plus beta z plus gamma p. Crowley-Martin functional response that takes the form of alpha p upon 1 plus dp plus bz plus bdpz. Then there is Evlev type functional response, that is alpha p 1 minus e power minus beta p. Another one is Evlev-like functional response. Here we don't have this term 1 minus, so it is alpha p e power minus beta p. And then there is linear ratio dependent, that is just alpha p upon z, with this term in the denominator that is missing, alpha beta p, which we see in the standard ratio dependent functional response. So the details of these functional responses can be found, and the meaning of this individual parameters in detail can be seen in these two references. Okay, so now that we have considered, we have seen basic mathematical models studied in ecology. Now there are different goals that are taken into consideration as a problem for mathematical ecologists, which they solve through these mathematical models. So what are those goals or problems that mathematical ecologists discuss? One of them is understanding or studying the chaotic dynamics in the mathematical model. So what is that? What is this chaotic dynamics? Let us discuss it in brief here quickly. And how do the mathematical ecologists study it? So first of all, chaos is an aperiodic long-term behavior in a deterministic system. which exhibits sensitive dependence upon initial condition. So we must understand here that there is no well accepted definition for chaos so far, although people have tried to define it in certain way, and this particular definition has been proposed by Stephen Strogatz. So it tells that it is property of a deterministic system, and of what type. So whenever it shows sensitive dependence upon initial condition and it's an aperiodic behavior over a longer period of time, then it is termed as chaos. And chaos is very widely studied in ecological models. So in order to study chaos in any mathematical model, one has to consider a continuous dynamical system, and your dynamic system has to be of degree 3 or more. Otherwise, the chances of having chaos is negligible in the mathematical model, or in fact it will not occur at all whenever the degree of the system is not at least 3 or more. So this corresponds to, just now we are talking about two species mathematical model. So it corresponds to the interaction of 3 or more species, so which we haven't studied so far. So I'll be showing some 3 species model in the coming slides. And as I said, also one of the famous theorem in nonlinear dynamics known as Poincare-Bendixson theorem. This also ensures or suggests that a solution of 2 species model systems either converge to a point or to a closed curve, and hence it's impossible that chaos would occur in a 2 species model system. So keeping this in mind, let us move to 3 species food chain model. So some of the very popular 3 species food chain models, I'll just talk about 1 or 2, and then I'll come to one of the 3 species mathematical model that our research group has studied. So here this 3 species food chain model presented in equation number 11. Here this is X is the pre-population density, Y is the intermediate predator population density, and Z is the top predator population. So here we have assumed that Y is the specialist type predator and Z is the generalist predator population. Now here we see that the growth of the prey population here is again governed by the same dynamics as we discussed earlier. That is, A0x is the natural growth in the prey population, B0x square is a decline in the prey population due to intraspecific competition, and this is decline in the prey population due to predation by the intermediate predator Y. And what is added here is that earlier we had just one predator, here we have 2 predator in the picture. So Y is the intermediate predator, which is again eaten by the top predator Z. So growth in the intermediate predator population Y is given by this particular term V1xy upon D1 plus X. So just now we discussed about the functional responses. So this is of Holland type 2 as discussed earlier. Then again Y is eaten up by the top predator population Z, again using the Holland type 2 functional response, and this is the death rate of the intermediate predator Y. Its natural death rate. And again, since Z is of generous type, hence this growth is modeled by the term C3 Z square, which was proposed in this particular these 2 papers. So growth of a generous predator can be modeled using quadratic growth term, which was given here as C3 Z square, and minus this is the decay of the top predator population given by this particular term V3 Z square upon D3 plus Y. Now here in this particular mathematical model, it is studied in the literature that this is a very dynamically rich mathematical model, as it can be seen from this figure. So there are existence of strange attractor in the mathematical model as seen from this first figure with the phase plot of xy. Then also it has change. There is a bifurcation in the mathematical model which we can see from this particular figure where a naught is the bifurcation parameter, and this is the attractor that is plotted for this particular mathematical model. So here we see that there is and also authors have seen chaos in this mathematical model when we have three species population model with the top rater being the generalist type. Let us move to the next three species mathematical model. So this is also studied in literature. So here your top rater, how is it different from the previous case? In the previous case, the top rater which was which was considered is of type generalist type. In this particular model, the top predator is of specialist type. So here X is the prey population, Y is the intermediate predator population which is of specialist type, and Z is the top predator population which is again considered to be of specialist type. So the dynamics of the prey population and the dynamics of the intermediate predator population is exactly the same as in the previous model. However, we can see the change in the dynamics of the top predator population in the sense that here this minus CZ is coming, which is the death in the top predator population in the absence of its favorite food, which is obvious since Z is your specialist type top predator. And growth in the predator population Z is happening due to consumption of the intermediate predator Y, and it follows the Holling type 2 functional response. So what is seen in this particular model is that so it's a three species model, and this here initially there is a stable focus in this mathematical model which eventually changes to a limit cycle by changing the sensitive parameter involved. I am not getting into the detail of the sensitive parameter here or other dynamics that is seen here or the goal of this particular article. My goal of showing this mathematical model here is that what are the different types of models which exist in literature for understanding ecological systems, and what are the different problems that authors address while discussing such type of mathematical models. So here in this particular mathematical model where which is based on the intermediate predator being specialist and the top predator being specialist as well, here it was seen that initially there was a stable focus, and this dynamics, it was dynamically very rich model, and by changing certain parameter values a limit cycle was seen, and then a chaotic attractor was finally seen, and it was period and the route to chaos was a period doubling, which is seen from this figure C. So this was another three species food chain model which is being studied in literature. Now this is a Hastings-Powell mathematical model which was proposed in 1991, and here in this Hastings-Powell model your X is the number of species, number of prey population at the lower level of the food chain, Y is the number of species that preys upon X, and Z is the number of species that preys upon Y. Now the growth of, again here the dynamics of this prey population and the intermediate predator population is the same as we discussed earlier. However, the top predator Z, we can see here that this is the death is minus of type minus T2Z, which is a decline in the predator population due to the absence of its favorite food, and here this is again the growth in the predator population which follows Holland type two function response, and it is due to the predation of the intermediate predator Y. So this is Hastings and Paul model, which is being studied in literature, and this this model also exhibits chaotic dynamics, as it can be seen from the time series shown here, and further the chaotic attractor also is seen in this Hastings-Paul model. Cup type attractor is seen in this mathematical model. Now this is one of the work that we have done. So, and it is very interesting because this particular problem opens up another dimension of studying this ecological models in literature. So as I was mentioning earlier, that one of the major goals of studying this ecological model is understanding the dynamics of that particular model. Another goal of studying such ecological models is to understand the distribution of the populations in space, or in simple words, how these populations are distributed in a particular region or locality wherever they exist. So that is done using the pattern study of these population into consideration. So in this particular mathematical model that we have considered, the basic structure is of Hastings-Powell type, and what we have done is that we have introduced refugia and alley effect in this mathematical model, and our goal was to see the pattern formation in the mathematical model, is if there is any pattern formation in these populations, and also to understand the if there is any significant effect of alley effect and refugia on the dynamics of the mathematical model. So here the refugia is being introduced using this particular term here, as we can see. So what is M here? So it is assumed. What is what do you understand by refugia? So it is whenever a small portion of the population is able to escape predation, that is termed as refugia, and this can be supported by environment or other possible ecological factors. So here we have assumed that a small portion M of the prey X, it always escapes the intermediate predation Y, and that's why this term is coming here in this first term, that is A1 1 minus M XY. So what is happening? The remaining 1 minus M portion only takes part in the interaction with the intermediate predator Y. That's why here we have considered 1 minus M times X into Y. And here also 1 minus M of X. So this is how we can incorporate different ecological factors in the mathematical model. For example, just now as we have incorporated the refugia effect. Alright. Then next we have considered alley effect in the prey population, here as shown by theta. So here we have assumed weak alley effect. So weak alley effect is incorporated in the model using this term x upon x plus capital theta. So rest all details of this dynamics of this model is same as explained just now in the previous slide of this standard Hastings type model, Hastings and Powell model. Now this particular mathematical model, we have, first of all, what we have done, we have, in order to reduce the number of parameters involved, as if there are number of parameters are more, it is difficult to understand the impact of these parameters on dynamics. So therefore we have non-dimensionalized this mathematical model in order to reduce the number of parameters, and hence we obtain the mathematical model in this particular form as shown in equation 15, and non-dimensionalization of the parameter has been done as per shown here. So here we have studied the dynamics of the proposed mathematical model in the absence of refugia and alley effect both. So what do we see here is we have considered this parameter B1 here, this parameter B1 to be the sensitive parameter, and with respect to this bifurcation parameter B1, it is seen that initially there was a stable dynamics, and later there was a period doubling which was seen here, and then it led to chaotic dynamics. So we see that in both prey and the intermediate predator population, as well as in the top predator population. And we see this result, this presence of this bifurcation and stable dynamics changing into chaotic dynamics in all the three populations in the absence of refugia and allele effect. Further, we see the time series of all the three populations: prey, intermediate predator, and the top predator population. So, and also we see the attractor which we obtain for this particular mathematical model, which shows a strange chaotic attractor as seen from this figure here. Now, as I mentioned earlier, that one of the goals is also to understand what is the impact of these ecological factors on the dynamics. So, with that motive in our mind, we try to see the effect of allele effect, the impact of allele effect on the dynamics. So does it have any effect on the chaos present in the mathematical model, and does this allele effect can actually control chaos, and which is one of the very popular problems in ecological dynamics, to control this chaos. So what we saw is that this theta is the allele effect. So when we increase initially there is a chaos in the mathematical model, but as seen in earlier simulation as well, that the stable dynamics changes into chaotic dynamics. Now when we have this chaotic dynamics and when the theta is introduced, and as the value of this theta increases, this chaotic dynamics changes into stable dynamics, as it can be seen from this figure. Then intermediate predator, also we see the similar pattern. The chaotic dynamics changes into stable dynamics as this allele effect changes or increases. Then in the top predator population as well, we see that as the theta value of theta, as we introduce theta into the model, which is your allele effect, and as we increase its value, the chaotic dynamics changes into stable dynamics. Now this can also be seen from this phase portrait or the phase space plot. So what do we see here is that initially there is a chaotic attractor seen in the system, and here we are increasing the value of this allele effect theta, and we see that this chaotic attractor shows a period 2 limit cycle, and then there is a limit cycle that is seen, and eventually it converges into a stable focus, as it can be seen from this figure. Now further we attempted to see what is the effect of this refugia on the control of chaos. Can this refugia also can control chaos? So as we just now saw that allele effect has a significant impact on the chaos control. It can actually control the chaos present in the model system. So here the refugia parameter M, it was considered as one of the bifurcation parameters, and we saw the change in the population, three populations: prey, intermediate predator, and the top predator. So the refugia effect, as it is introduced and as it is increased, the chaotic dynamics changes into stable dynamics, as it can be seen from all the three populations. Also from the phase space plot, we see that initially there is a cup type attractor, chaotic attractor seen for the mathematical model, and as the refugia is introduced and the value of M is increased, we see that this chaotic attractor changes into limit cycle, and finally it changes into stable focus. So what is seen here is that both refugia and allele effect can actually significantly impact the chaos control in the mathematical model. It can actually cause control of chaos in the mathematical model if chaos is present in the model system. Now this is another model that we have studied. So this is the basic backbone of the mathematical model that we considered, which was given by Friedman and Ruan. So here we tried to see what is the effect of group difference on the model, and also how to model the group difference, how to incorporate the group difference in the mathematical model. So what is actually group difference? So it is a phenomenon seen in the prey population in response to the predator population when they attack on it. So what they do is that they defend themselves using group defense property, and this can be seen in the musk ox population, and there are many other population as well where we see the group defense. So what has been seen in literature is that Holic type 4 functional response and simplified Holic type 4 functional response, Iblov type functional response, and Iblov-like functional response, all these functional responses are being used to model group defense in the prey population. But there are rarely any studies where this group defense is studied in 3 species food chain model. So what we did, we tried to see that how can we model the group defense in 3 species population model. So for that purpose, we considered this standard mathematical model where the growth, this is the prey population growth, and this is the decay in the prey population. That is here P of U1 is the functional response to be considered, which will, so what we did, we replaced this P of U1 by the Iblov-like functional response in order to model the group defense. So this is the mathematical model that we considered in our study. So here we can see that this alpha u e to power minus beta u1 is a Iblov-like functional response that we considered, and it models group defense in the prey population. So this is here it is coming as again alpha 1 u1 u2 e to power minus beta u1. Now as we can see, this Iblov-like functional response is a non-monotonic functional response. Alpha u e to power minus beta u is a non-monotonic functional response. Now let us understand various factors in this mathematical model. So R is the birth rate of the prey, K is the carrying capacity of the prey, and A is the half saturation constant here, small a. This is your half saturation constant of the intermediate predator as shown here. Alpha 1 is the conversion coefficient from prey to the intermediate predator, and from prey to intermediate predator. Gamma 1 is the conversion coefficient from intermediate predator to the top predator. Gamma 1 here, this one. Now D1 is the death rate of the intermediate predator in the absence of prey, and D2 is the death rate of the top predator in the absence of intermediate predator. Now we have studied this mathematical model in a specially extended form, because one of the goals of the study was also to understand how these populations are distributed in spatial domain. So this is another research goals in many of the ecological studies, to understand how these populations are distributed in spatial domain. So we consider this positive initial condition and zero flux boundary condition for studying this spatial extended mathematical model mathematically. And the domain that we considered was a square domain in R2, that is 0L cross 0L. So we studied this mathematical model, and we saw the change in the transition in the dynamics of the mathematical model. So what we saw that when this beta term, it was which was one of the sensitive parameters, when this is changed, actually this is increased, then initially there is a stable focus dynamics in the mathematical model. So the stable dynamics changes into limit cycle, and then it changes into the period 2 limit cycle, and then finally it changes into chaotic dynamics at beta equal to 0.11. Also at beta equal to 0.15, the extinction of the predator population was also seen, which is one of the phenomenon that is seen in ecology when there is a group defense by the prey population. Now we here studied both the temporal system as well as the spatial extent model system, and we investigated the presence of chaos in the in both the mathematical model. So by temporal model I mean this equation number 19. This mathematical model we investigated and we saw existence of chaos in the model, and the spatial extent model is this equation 21. So here we saw that this time series there of chaotic nature, and the attractor that we found, it was also strange chaotic attractor seen in the temporal mathematical model given in equation 19. Now this is the dynamics that we observed for the spatial extent system, and we saw that initially there was a stable dynamics, and eventually it led to a chaotic attractor which was obtained from the space series of the mathematical model. So the space series is shown here as a chaotic nature, and its corresponding chaotic attractor also is presented. So here we started at the number of simulations which was done was at equal to 500. When we increased the simulation time to 1500, we saw very clear strange chaotic attractor in the mathematical model, spatial extent mathematical model. Further, we studied the patterns present in the mathematical model. So for that purpose, what we did, we perturbed the initial value with a very small perturbation in the prey population and the top predator population. So the initial condition that was considered is of this particular form. And we also considered, we investigated the pattern formation in both one dimension and in two dimension. So in the two dimension, this was the initial condition that was considered with the other values fixed at this particular value as shown here, and in one dimensional case this was the perturbation considered. So here what was seen that we fixed all the parameter values as shown here for the simulation, and we were changing the value of the diffusion coefficient in the three population, that is prey, middle predator and the top predator population. So the diffusivity coefficient in the prey population is delta 1, diffusivity coefficient in the middle predator or the intermediate predator is delta 2, and the diffusivity coefficient of the top predator is delta 3. So we are changing these, and we saw that and also the beta, another parameter beta was changed, and what was seen is that we saw an extensive range of spatiotemporal patterns as well as Turing patterns was seen, which is presented in this figure. So here what do we see that this first figure, it shows spatiotemporal patterns. In the first column is for the prey population, the second column are the spatiotemporal patterns obtained for the intermediate predator, and the third column is for the top predator population. So the parameter values are already shown earlier in the table, and what we are doing is that we are changing the time for simulation, and here when the simulation when this simulation was done for equal to 500, this was the pattern of or the distribution of the species which was seen in the spatial domain. And as we increase the time, we see that these patterns are changing with time, which are spatiotemporal patterns. We can also see how this is evolving with time. So we can see here from this movie that the prey species, as the time increases, this prey species converges to a type of patterns which shows how this prey population is distributed in a spatial domain with time. So as we can see here, the prey population is very well distributed in the spatial domain, and it shows how we have reached to figure D from A. It covers all the intermediate distribution of the prey population over time. Similarly, we can see for the intermediate predator and the top predator as well. Now, here in the second figure, what we did is that we changed the value of the diffusion of the top predator population, that is delta 3. So it was delta 1 and delta 2 was kept same as in this figure, and the delta 3 was changed to 0.1, and other parameter values remain same. So we see that a different set of spatial optimal patterns are seen here in the first column for prey population as compared to the first column here for the prey population, and then the second column for the intermediate predator, and the third column for the top predator population. And also we can observe the progress of this distribution of the population on a spatial domain with the help of following how these populations are changing in a spatial domain with the help of this movie that anyone can see using simulation. Now here again we further change these value of diffusory coefficients, and we see another set of spatial temporal patterns in prey population, middle predator population, and the top predator population. Here what we have done, we have again changed the value of delta 3. So the delta 1 is 1, delta 2 is, we have also changed the value of delta 2 as well, and delta 3 as well. So we see another set of spatial temporal patterns. Again, in this particular figure also, we see that these patterns are changing as we change the diffusory coefficient. So here we have reduced the movement of the middle predator population. So from 0.01, we have changed delta 2 to 0.0001. And delta 3 was 0.0 earlier, we have increased it to delta 3 equal to 1. And we see that a wide range of patterns are being, of the spatial temporal patterns are being seen in this mathematical model. Further, we have also seen a Turing pattern in the mathematical model, as it can be seen from these two figures. It's a one-dimensional Turing pattern which was seen, so it's a ripple type Turing pattern, and this is a vertical stripe Turing pattern was seen. And in the two-dimensional domain as well, we saw a range of Turing patterns, as it can be seen here. So here we see that initially the prey species distributed well throughout, but eventually as the time increases, it starts taking form of a very regular form of the distribution, and eventually we see a Turing pattern of this particular type which is presented in that figure, and further it changes into patchy type Turing pattern as seen here, and which becomes stationary after time t is equal to 4000. So we saw a very wide range of Turing patterns as well here. So what do we saw from this study is that this is another very interesting problem to understand in ecological models, that how this prey population, intermediate population, and the top predator population, how they are distributed over a particular region or locality wherever they exist, and what is the impact of various ecological factors on the dynamics of these population into consideration. So this was a small brief of the mathematical models that we study in ecology, and what are the goals in mind while studying these mathematical models, and what are the different basic mathematical models that we consider for studying such ecological problems. So that is all. Thank you.